Hello everybody. Today I will be talking to you about chelating agents, chelation therapy, and their potential links to future cancer treatments. The three main vocabulary words that will be reoccurring in this topic today are chelating agent, chelate compounds, and chelation therapy. A chelating agent is a substance whose molecules can form several bonds to a single metal ion. An example of a chelating agent is EDTA. Because of the lone pair of electrons available on both the nitrogen atoms, EDTA is able to function as a multidentate ligand and form two bonds to the central metal atom it coordinates to. A chelate compound is when a metal ion and a chelating agent are bonded to one another. An example of a chelate compound is when EDTA bonds to Fe2+, and this creates an iron 2 EDTA complex. Chelation therapy is the administration of chelating agents to remove heavy metals such as mercury and lead from the human body. Chelation therapy has typically been used to treat heavy metal poisoning, but many researchers are interested to see if it would work in the treatment of other diseases, such as cancer. A study was published by Whitnall et al. Out of the University of Johns Hopkins School of Medicine in 2006 titled, "A Class of Iron Chelators with a Wide Spectrum of Potent Anti-Tumor Activity that Overcomes Resistance to Chemotherapeutics." The researchers' idea was to deprive cancer cells of essential nutrients that they need for DNA synthesis and replication. Iron is a metal that is key to DNA synthesis since it is a major component in ribonucleotide reductase. Ribonucleotide reductase is very important in the human body because it is a key enzyme that is necessary for DNA synthesis. Another important facet of this enzyme is that it is iron dependent. This was important for Whitnall et al. For their study because they wanted to find a chelating agent that would be able to bind to a metal that is important in terms of cancer. And if they could prevent the DNA in the cancer cells from being synthesized by targeting its iron dependence, then they could potentially create a new way of treating different cancers. In a subunit of the ribonucleotide reductase known as the RnR2 subunit, there are ligands specifically that iron bonds to, and some of these are carboxylate ligands. The specific one in the RnR2 subunit that iron bonds to is known as aspartate. The two negative charges on the aspartate ligand are attracted to the 2+ charge on the iron, and this creates a complex for which we can write the equation as follows, and this can describe how the iron aspartate complex is formed. We can represent the formation of the iron aspartate complex with the formation constant shown in the current slide. In their study, Whitnall et al. Wanted to find a chelating agent that would effectively bind with Fe2+, and would thus prevent Fe2+ from assisting in the DNA synthesis of DNA in cancer cells, and therefore it could be used, these chelating agents could be used as an effective cancer treatment by preventing cancer cells from replicating. The researchers found that chelators that had a DPT backbone were the most effective chelating agents. Specifically, the DP44MT ligand showed the most effective anti-tumor activity. In their study, the researchers added 0.75 milligrams of DP44MT for every kilogram of body weight. Using the deviant equation, we can calculate the female ideal body weight for a woman who is 5 foot 7 inches tall. Her ideal body weight comes out to be 61.6 kilograms. Using this weight and the knowledge of how much DP44MT is being injected into the mice per day, we can calculate that 46.2 milligrams of DP44MD would be given to a patient every day. Using the amounts of DP44MT and Fe2+ that we have, we can calculate the amount of moles of each of those that we have in our body. For the female that we have already weighed, we can calculate the volume of her body. From knowing these two pieces of information, we can calculate the concentration of iron 2+ and the concentration of DP44MT in this woman's body. Using these concentrations and the given concentration of 4 moles per meter cubed of the Fe2-DP44MT complex, we can calculate the formation constant for our complex, which comes out to be 5.26 times 10 to the power of 4. The larger the formation constant, the more stable a complex is. Therefore, if the formation constant of the iron 2 DP44MT complex is larger, then it will be formed over the iron becoming involved with DNA synthesis in cancer cells. To review, the use of chelating agents is to create chelate compounds, and this is the purpose of chelation therapy, to bind strong metals with chelating agents in order to rid them of the body. What some scientists are now working on is using chelating agents to treat cancer. They are working on finding chelating agents that can target specific metals that allow cancer cells to proliferate, such as iron, which allows DNA synthesis in cancer cells. By being able to control how that iron interacts with the cancerous cells, scientists are hoping to be able to use chelation therapy as a sort of cancer treatment in the future. Thank you for tuning into my video about chelating agents and their potential use in the treatment of cancer. I hope you learned a bit and that this video was enthralling and enticing for you. Have a wonderful day!